that's actually what is going to be applied to the Kinarm robot. It's not the force or torque that's actually being applied to the subject. Now under static conditions, so if we go back to Newton's laws, so if there's no acceleration, then the force applied to the robot will be the same as the force applied to the subject. So under static conditions, it's exactly equal. But when the robot is moving, then Newton's laws dictate that there will be some differences because some of the force or torque that's being applied to the robot is going to be producing acceleration movements in the robot, and the rest of the force will then be applied to the subject. So there's a little bit of a subtle difference. And the reason why that's the case rather than being able to command the actual torque to a subject is because that's actually very technically challenging. It requires something called inertial compensation. And although you might come across papers where people claim to provide inertial compensation, usually there are some caveats that they either don't talk about, or if they do talk about it, it becomes quite complicated. But anyway, again, for most situations, it doesn't particularly matter, but it is a useful little bit of detail to know and understand that when you do command a force or torque, that's what's being applied to the robot. If you, or when you go back to Simulink and you open up the Simulink library browser and you go to our dexterity library, you'll notice that there's these sub-libraries. So this morning, Duncan was talking about the blocks in the video sub-library, and now we're going to be talking about the loads library. And just to point out that there are two different sub-libraries. One is for the Kinarm endpoint robot, and one is for the Kinarm exoskeleton. So depending on which robot you want, or which robot you have, you're going to want to use the loads from the correct sub-library. This is what the two libraries look like, and they're actually very similar in terms of what types of blocks are in there. The primary difference is that the exoskeleton will have loading blocks related to both hand-based coordinates as well as joint-based coordinates, whereas the endpoint robot, joint-based coordinates doesn't really make any sense, and so they've only got the hand-based or the endpoint-based coordinate system. And I'm going to go through some of these blocks in a little more detail later. But in terms of the basics, when you apply or you want to apply some sort of load to the Kinarm, the first thing is you need something that's going to create a command specification. So in this case, this is a constant loads block. The torque command is just going to be a constant torque coming out of this. And then there also needs to be a Kinarm apply loads block, which is the block that processes the torque command and then actually commands the motor system to apply it. So again, you have to have something that creates a specification and another block that actually applies it. I'm going to look a little bit more detail in terms of what's actually in and how you use these blocks. If I were to double click the apply loads block, then I get this kind of dialog pop up. And there's not a whole lot on here, but there's a couple key parameters. One is that you can set up these ramp up and ramp down durations. Those have a very limited scope in the sense that they affect what happens at the start of a task, what happens at the end of a task, what happens if you pause or restart a task. And the idea is that we want to make sure that torques and forces get ramped down smoothly. Turning forces on or off abruptly can be really disturbing and startling to your subject, and so it's typically not something that you want. And so putting these numbers in here will have no effect on your experiment because it's just at the beginning and the end. It doesn't happen in the middle of trials or between trials, but it also ensures that the system behaves nicely. The second parameter I want to point out is this torque limit. And what this does is this allows you to set an upper bound on the magnitude of the forces or torques you're going to apply. So you may decide to limit it or constrain it to some lower level for a variety of reasons. One reason is when you are developing a task and you're testing things out and you're maybe not so confident that all your code's working, you might want to put a low limit in here so that regardless of what value you create in your specification, it'll get clamped to some small value. So then it doesn't matter if you make a mistake when you go to first test out your task. You'll be protected by this torque limit. A second reason you may want to do this is that the Kinarm robots have a maximum torque that they can produce, but that's only for a short period of time. So for the Kinarm endpoint robots, for example, that's about 57, 58 newtons. They can only do that for a few seconds, after which the system will disable itself to avoid overheating. If you cut that down to a third, so around 19 newtons, then that can be done indefinitely. There's no time limit. The system will never overheat. And of course, there's a scaling in between those two values. And so you may have a task where you want to ensure that the system never overloads or goes into a state where it needs to try to protect itself. And so you might want to limit the torques or forces in that situation to avoid that possibility. The other block, in this case, the constant loads block, if I were to double click on it, this is an example of what the dialog actually looks like. And so as with all of our blocks, the dialog has a description followed by various parameters that you can set and change. So up here, you can see that we have a description which says that force in the X direction and force in the Y direction are going to be defined by A and B. Well, where do we get A and B from? Well, this block works in a similar manner to the show target block, where what we're going to do is here we're going to define which columns in the load table we're going to look at, because the row is going to be defined by the input. This is the same thing we saw before with the show target block. So if I were to look at an example of a load table, so this is from a task protocol that you can edit in Dexterity, you can see that in this case, if the input row was equal to 1, then the way I get this from the load table is that means I'm going to look at load 1, which is this first row here, and I'm going to look in column 1 for the value of A. So A is going to be negative 0.5, and that's what my force in the X direction is going to be. And then B, I'm going to look in column 2, which is in this case 0, and so that means I'm going to have 0 force in the Y direction. So this is that same sort of referencing where you define the columns here, you pass in the row here, and then it goes and uses that to look up the values in the load table. That's the same dialog. I just wanted to focus on one of the parameters, and that is this load on arm to be assessed. So what this means is that when you go to run a task in Dexterity, one of the things you always do is you have to select, well, is this the right arm being assessed or the left arm being assessed? And what this checkbox does is this indicates which arm you're going to be applying the load to. And that way that you can have a task work both on the right arm and on the left arm without having to make a new task protocol or define anything. It just automatically happens. If I want to have loads on both arms simultaneously, then I would need to have 2 copies of this block. One copy where this is checked, so that's going to produce a load on the arm to be assessed, and one copy where this is unchecked, which means that the load will be on the contralateral arm. At the bottom, you'll notice there's this other option about using a left-handed coordinate frame. And this is, again, similar to what we see with visual targets. In that case, with the visual targets, the using left-handed coordinate frame was defined in the task protocol. Here, it's defined actually in the specific block. And again, what a left-handed coordinate frame means is that positive X is going to be to the left instead of to the right. So again, this means that when you take a model that and a task protocol, and you've developed it maybe for the right Kinarm, if you want it to be act in a mirror image fashion on the left arm, then you would have this checkbox checked. Often it's convenient to be able to scale loading conditions in various fashions. And as with any type of programming, there's lots of different ways to solve this problem, but we've provided a mechanism which for most cases will make things a little bit easier. And you'll notice that in the dialog, so this is the dialog for the constant loads block, there is an option called source for scaling. So it was defined here in the dialog, but if I select port from the drop-down menu, you can see that a new input comes in. So what this means now is I can pass a variable in, so I can dynamically control the scaling. So instead of just having a constant load, that means I can scale it up and down at my convenience. That could be useful for scaling things on and off for, say, part of a task. Maybe at the beginning of the trial you have it on and then you slowly turn it off, or from one trial to the next. But it also is useful for perturbations. One of the other blocks that we have in our TDK is this what we call perturbation block. And what the perturbation block will do is when it gets triggered to run, it'll create a time-based profile. So it's a trapezoid. It'll go from 0 up to 1 at some point, and then it'll scale back down. The duration of the ramp up, the duration of the time at 1, and the duration of the ramp down are all going to be set via values in the load table. And then, so this is what that scaling output looks like. So it gets passed into the constant loads block. So for example, if the constant loads block was producing a 5 Newton load, then when you put in the scaling input from the perturbation block, the output then of the constant loads block looks like this. So now I would get a torque or force perturbation that scales up from 0 up to 5 over a certain time period, stays at 5 for that time period, and then ramps back down again. So this is how we can create perturbations. Velocity load blocks, we have a couple of those, and they're in many aspects very similar to what we saw before for the constant loads block. So for example, we always have this definition at the top in our dialog that explains what are the parameters and how are they going to influence force. So in this case, we have A, B, C, D, which are going to act on the X and Y velocities to produce force in the X and the Y direction. So the parameters A and D are really controlling the viscosity. So viscosity, of course, is force that resists a motion in the given direction. So what are B and C? Well, those are actually parameters that can produce curl fields. So in both cases, velocity in one direction, say the Y direction, will produce a force in the perpendicular direction. So B is velocity Y affects force in X. C is velocity X affects force in Y. And beyond that, this all behaves the same as the other block we looked at. So where do we find the values for A, B, C, and D? Well, we have to look in the load table, and here is where we say which columns of the load table are going to find it. What's the row? Well, again, the row is passed in to this block via this input, and so that's how we know which row in the load table to look at. Let's imagine that you want to do something unique, something different. It's very often that people want to have some sort of custom loading condition. And rather than just start from scratch, what you may want to do is look at what we did and maybe start with a block that we have and modify it, customize it. If you right-click on any of our blocks, you go to select mask and then you look under the mask, what you'll see is the code that we have implemented to create that block. So that's what's shown here. And in most cases, what there is there's a number of sort of inputs and outputs that are all feeding into and out of some sort of embedded MATLAB, and that's what's been highlighted in the middle here. If I focus on that a bit more, so this is that embedded MATLAB code. I'm just going to point out a couple of the things that are being done. You'll notice that we're passing in the load table. So this is that entire table that is defined, that's entire load table defined as part of the task protocol. We pass that in. We pass in the load row because that was an input to this block. And then we can pass in the column indices, which are defined by the dialog. And so this is how we can write code for accessing values in the load table. Likewise, we can access information, for the velocity dependent loads, of course, we need to know what is the velocity of the Kinarm. And so there is this structure called the KinData bus, which is part of a go-to-from tag. And this allows us to get all sorts of information, including, for example, the hand velocities. And so we can pass those in to our embedded MATLAB code. And then that allows us to write embedded MATLAB code like this down here. So I know that was a lot of information I just presented here. The most important thing is if you right click on one of our blocks, look under the mask, you can go see what we did. And that allows you then to take advantage of all the kinds of structures and stuff that we've set up to be able to create new and interesting loads. We often get asked the question about having multiple loads at the same time, and the short answer is yes. So here's an example where we have two different types of loads going on. We're going to have a velocity dependent load, and then at some point in time, there's going to be a perturbation applied. So these are the things that are creating the torque command specification. And so each of those, the torques just need to be added and then sent over to the Kinarm apply loads block. It's important, there can only be one Kinarm apply loads block in your model, all right, because you've only got one Kinarm robot. So all of the torques that you want to add on simultaneously, you just need to add them together to apply them to that one Kinarm apply loads block. I'm going to talk just a bit briefly about position control. This is something that lots of people are interested in. Up to now, I've been talking about blocks that are applying torques of some sort. So you're defining a force field or a perturbation or a specific torque magnitude. For position control is different because what you're trying to do now is you're now controlling the position of the robot. You're not controlling the torque. So what this block does is it figures out what torques it needs to do in order to control the position. Again, this is a block that is found in our TDK. And the important thing is that the input, so the desired XY position, that's the input which specifies where you want the robot to be at that instant. So a lot of people often think that, oh, I'm going to say I want to be over there, in a second or so. That's not what this is. This is saying where I am at that instant. So if you want to move from one position to another, then what you need to do is create a trajectory. So some sort of time-based profile, and you feed that in one position at a time, each time step into this desired XY position. So that trajectory gets fed into this one time step at a time, and this controller then basically moves the robot along that trajectory. This is an advanced block to use. I don't suggest you start playing with it today, but if you do start wanting to play with it, the best thing to do is to go look at some of the sample tasks on our website. We have a whole bunch of sample tasks on there, and in particular, we have two that are related to position control. They use the block in slightly different ways, and it is far, far simpler to start with a model that already works, already has some of the functionality that you want, because then you can really look at it and understand, okay, how did they use that block to do what they did? Because once you understand that, then you can figure out how do you modify it and customize it to make it do what you want to do. Couple things to point out. One of them is the Simulink real-time scope. This is a wonderful tool. I know Duncan introduced it yesterday, and in particular, when you're playing with loads, this is a great time to be using it because what you can do, you can feed in the torque commands that you think you want to apply to the robot, and then you can look at them on a scope to find out, are they even vaguely correct? That's a much safer way of doing things than just putting them on the robot and discovering that maybe you were off by an order of magnitude by accident. So very useful tool. And as Duncan mentioned yesterday, you can have scopes that produce graphical input. You can also, or output. You can also have scopes that produce numerical output. And particularly with loading conditions, I often will put both types of scopes on my screen because the numerical ones are really good for giving magnitude, but it's kind of hard to sort of see a time profile, particularly with a perturbation. Whereas if you put a graphical scope on, well, then you can actually see the waveform as it happens, and that'll really help let you verify that you've got the time-based information correct. And another friend, just to remind you, is also the emergency stop button. Again, this is particularly relevant when you're using and playing with loads. If you're applying a loading condition for the first time and you're testing the system on yourself, you want to be able to have a way to turn things off just in case you've made a programming mistake. This is always a very important thing. If you are testing out loads, the other thing I'll mention is particularly with the exoskeleton, never test it out without somebody actually in the robot. Our robots are quite light and it doesn't take a whole lot of force for those robots to be accelerated and move at a very high speed. Easy for you to overcome if you're actually in the robot, not so easy if you're not in the robot. So always make sure that someone's in the robot, the exoskeleton, when you're testing out loading conditions. This is the same slide I showed earlier, again with the blocks in our TDK. So we have the endpoint blocks and then the exoskeleton blocks. And again, the kinds of blocks we have in here, we have some for producing constant loads. We have some for producing velocity dependent loads, perturbations, the position controller, and each of these has an apply loads block. So you have a Kinarm EP apply loads block, and separately you've got a Kinarm exo apply loads block. And again, just make sure that you use the correct blocks for your particular robot type. And of course, as with all of our blocks, when you drag them into Simulink and you want to know how to use them, you double click on it, which brings up a dialog, provides a bit of information, but also there's that help button in there too, which gives even more information and details about the inputs and outputs and how they actually get used. A couple thoughts just to keep in mind. The most important thing is that the robot does what you have programmed it to do. So if you program a load to turn on at 10 Newton meters at some time, then that's what's going to happen. It'll go from 0 to 10 newtons in an instant, which is really not nice for the subject. So if you are going to apply a very high load like 10 Newton meters, and if you want it to be ramped on, you have to program that ramp on. The system doesn't know what you want. It only knows what you've told it to do. But the same is also true for turning things off. Going from 10 back down to 0 is just the same as going from 0 to 10. It's a change of 10 Newton meters. So again, you want to turn these things off in a more controlled fashion to avoid making your subject unhappy.